Hi guys, welcome back to Data Every Day. Today we're looking at a data set of a health insurance marketing campaign. So we have different customers who are being offered health insurance and a bunch of features about the customer. And at the end of the data, we have this column which is the response. Positive response indicates that the customer made a purchase of the health insurance product, and a negative response indicates that they did not. And we'll be trying to predict if a given customer will accept or purchase the product given these features. So let's hop into the notebook. We're going to import NumPy and pandas for working with the data. Let me just zoom up on this. So for visualization, we'll be using pyplot and seaborn. And we will use the train test split function and standard scalar from sklearn for preprocessing. And our model today will just be logistic regression, and we'll visualize the results using a confusion matrix and classification report from sklearn. So let's go ahead and import all of this, and we'll load in the data using pandas.read.csv. So we want to grab the CSV file path, which is up here. There's actually two of them here. And whenever you have a train test, you can just check the number of columns to see if they're the same. So we have one less column for test. This means that the target is not being included. And we don't, for our purposes, we don't have any need for this test set. It looks like this is some sort of competition where you would give the submission for the test set, and you'd create your own labels. Someone else who has the answers would judge it. But when you're when you want to analyze your model, you should be using a test set that has the target column attached. So we'll just be using train.csv today. I'm going to close these out and paste in the file path there. And let's load in the data and take a look. So here it is. We have 14 columns with the response at the end. And we can see we have a mixture of categorical and numeric. And so let us get some more information with data.info. Here we can see any missing values, and it looks like we have only 3 columns with missing values. You can see here. We also have 6 object columns, 6 integers, and 2 floats. Alright, so let's start pre-processing. I'm going to create a function called preprocess_inputs. And this is going to take in a data frame. For now, all it will do is copy over the data frame. So let's copy it into X. Let's store the processed data in X, and we'll pass data in to this function. So this is the copy of the data that we're going to do the pre-processing on. First thing I want to do is drop this ID column because it's not useful for making predictions. We know every value in this column is unique, which means there's no way to use it to draw similarities between the values. In any way, we wouldn't want it even if there was, because it's just a way of identifying a given example. So df equals df.drop ID from and we're dropping from axis 1. So there it's gone. So the next thing I'd like to do is take a look at missing values. We saw there were some. x.isNA will give us a true wherever there's a missing value. You can see they match up. We then sum over the rows to get the total number of missing values in each column. And there's quite a few in these columns. However, I don't know the proportion of the data that these are. For example, if we had 1,000,000 rows, these are probably nothing. So let's take the mean instead of the sum to see the percent of missing values. And we have 39% missing in these 2 columns and 22% missing in this. So I think the 39% columns are pushing it. I'm not going to leave those on. A good threshold is usually around 25%. If you have more than 25% missing values, you're better off dropping the column. But that's not hard and fast. You can definitely try it out. Try out different thresholds. But for the health indicator, we have 22% or 23% missing values. That one I think is just below the limit, so we'll keep that one on and we'll fill them. But these 2 we definitely have to drop. So let's say drop columns with too many missing values. So df equals df.drop. Again, this time in a list, we just put the 2 columns, and we're dropping from axis 1. Okay. So the remaining missing values are just in this one, which is health indicator. And before we fill the missing values, we should check what kind of data is in the column. So health indicator, and it's sort of these anonymous values. We don't know what they mean, but we know it's categorical. So when we have categorical data, the best way to fill the values would be to use the mode. So if you're doing a categorical column, this is a nominal column. We don't know if these have any ordering between them, so we assume that they're just independent of each other. Then one way to encode this is with getDummies. So pandas.getDummies will pass in that column, health indicator. And this will send each unique value to its own column, and a 1 represents the original value of a given example. You can see we have x1, x2, missing value. That corresponds to 1, 1, and then the missing value is encoded as all zeros. So one way to encode the missing values when you're doing this encoding is just to leave it like this. So you have all zeros to mean there's a missing value there. It's sort of there's debate about this, whether this is a good thing to do or not. Some people also will fill in a special value to mean missing, so that missing values get their own column as well. And then a final thing you can do is just to fill the value with the mode of the column. So for this video, I'm going to fill it with the mode, so we won't have any full zeros. But I will say that if you do that, you actually have some redundant information, because one of the columns will be dependent on all the others. Yeah, let me explain what I mean. If we have no missing values, so let's fill it. Let's fill missing values. We'll say fill remaining missing values. And so we're just doing it for this one column health indicator. So we're going to take the column and use fill NA to fill missing values with a certain value we pass in. The value we want here is the mode of the column. So I'm doing health indicator dot mode. And mode returns a series because there can be multiple modes. So let's just take the first mode with subscript at 0. And now if we run this, we should have no more missing values. They're all gone, no missing values. But if you run this now, you'll see that 1 has been filled in as the most frequent, which seems to be x1. So what I mean by redundant information is that one of these categorical columns actually is unnecessary, and it doesn't matter which one. So in terms of raw prediction, it doesn't matter with the kind of regression classification we're doing. But if you look what I mean, let's take x1 for example. We have a 1 if all the rest are 0, and a 0 if there's at least one 1 in the rest of the data. And that's the case for every single example. It's 1 if all the rest are 0, and 0 if there's at least one 1. So this is actually dependent on all the other columns. And you can say that about any one of these. So you can actually drop one. Now it's not super important, because most of the time having that little extra information can actually help the model. So there's a few cases where that's not a good thing to have. Just something to point out. So if we want to, I should also point out we can have a prefix on this. Let's call it health, and that would just put health at the beginning of each column name so that we know where these columns are originally coming from. All right, so next thing to do, I think, is because we finished with missing values. So why don't we do the encoding? So before we do the encoding, we should check what kind of values are in each column. So I'm going to create a dictionary that's going to map a column name to the number of unique values in the column. So I do x subcolumn.unique, and then take the length to get the number of unique values, and then we're going to do that for every column in x.columns. So we have to sort of be careful here. Okay, let's delete this. Let's look at x. So we have to be sure we know which ones of these are categorical. The reason I did all columns is because some of the categoricals are actually encoded as integers or as floats. Just integers actually. So you see region code, these are integers, but they are meant to be interpreted as independent values because they're codes. They're not meant to be seen as a continuous variable where one code is greater than another. So this should be one-hot encoded even though the values are not strings. So city code and region code are both one-hot. And so there's 5,000 values in this column. And as you could probably imagine, if we one-hot encode this column, we're going to end up with 5,316 new columns that we'd have to add to our data. And this can really slow down the model. You know, it really depends on what you want. For our purposes, we're going to drop it. There may be useful information here. It's just that I don't want to take too long on this video. So we are going to drop this because it's such a high cardinality column. So let's drop region code. I'll put it here. Drop high cardinality columns. Now, if you're going to drop a high cardinality column, you have to be sure that the column is actually categorical and not numeric. Alright, so it's gone. So the remaining ones, you see this one has a lot of values, but this is not categorical. This is numeric. This is the premium for the insurance. So we should not drop this. All the rest are fairly low cardinality, so we're good to go. So the next thing to do is to identify out of the categoricals which of them are of what type. So there's like mainly three types of categorical features, which would be binary features where there's only two values in them, ordinal features where there's more than two values but the values have some very clearly defined ordering, and nominal features where there's no ordering between the values and there's more than two. So it looks like we have three binary variables, which is accommodation type, RICO insurance type, and is spouse. And we know, okay, yeah, so these are categorical, and that means they only have two values in there. So the way you binary encode is just to send one of the values to 0 and the other to 1. Very simple. Let's just take each one. Let's start with accommodation type. And what we'll do is take the same column and call replace on it. And we can pass in a dictionary that has the mapping we want. So let's map rented to 0 and owned to 1. It doesn't matter which you choose, just as long as you send 1 to 0 and 1 to 1. In fact, it doesn't even matter if you use 0 and 1. You can use any two values. Because all the model needs is some way to judge which is which, like some directional feeling of the values. Okay, so we'll do the same thing for the other two, but we have RICO insurance type, which is the other binary feature. Paste that in, and its values are individual and joint. So let's map individual to 0 and joint to 1. And the last one is spouse, which is just yes and no. So let's actually confirm, because we can't actually see the yeses here. I assume it is, but we should just make sure. We check the unique values of the column. Yeah, it's no and yes. So let's map no to 0 and yes to 1. Alright, now you can see we have 0s and 1s in all three of these columns. Alright, so those are taken care of. The remaining columns to encode are the nominal columns. So we don't have any ordinal features in this dataset. So I want to point out just all the ones that are nominal. That's city code. These are not. These are numeric because they're actually ages. These are like numeric variables, continuous variables. Health indicator, this is nominal. RICO policy cat, I'm assuming this means category, and so that's actually categorical. This is also nominal, not numeric, even though it has numeric values. And then the last one's that's a response. We're not going to encode that. I'm going to keep that on the way it is. Okay, so it's just city code. Let's do this. One hot encoding. So what we'll do is iterate through all the one hot columns. For column in, and we have city code, health indicator, RICO policy cat, and that's it. For all three of these columns, we're going to do the one hot encoding. So first, let's create the dummy columns like we saw before. Pandas.getDummies for a given column, and we'll we'll give it a prefix like I showed before. That will just be the same as the column name. Then we'll take those dummies and put them onto the side of the data frame. So we'll use pandas duck and cat to concatenate together the original df and the new dummies side by side, so axis 1. And we'll go ahead and drop the original column from which we created the dummies. So we're dropping from axis 1. Alright, and that should be it. So we have 74 columns now. And you can see all of these are one-hot columns. So this goes to the end. But before that is our original data, and you'll see that everything is in numeric form now. So last thing to do would be to split and scale the data. So first we'll split. So we're going to split into x and y, where y is what we're trying to predict. So that's the response column. And x is the rest of the data. So we'll drop response from axis 1. Then we'll do our train test split. So that will give us x train, x test, y train, and y test. And we use the train test split function from sklearn. So we pass in x and y, specify our train size to 70%. Shuffle will be on, so this will shuffle the data before it makes the split, and we'll include a random state to ensure the shuffle is always done in the same way. And then let's return these 4 sets of data and get them back down here. Let's look at x train. We no longer have the response column, and we're dealing with 70% of the data. The test set has the remaining 30%. Y train is our classification labels. Let's look at the distribution of Y train. So we have more negatives than positives. So we may run into a bit of a class imbalance issue. All right. So last thing to do would be to scale the data. Right now, all the columns in our X take on different ranges of values, and this can confuse the model. So it can decrease the performance of the model. So we should have all the columns have the same range of values. So we'll use a standard scaler, which will give each column a mean of 0 and a variance of 1. So that's from sklearn, standard scaler. And we'll fit the scaler just to the train set, because we want to pretend we don't have access to the test set when we're doing the preprocessing. And then we're doing scalar.transform to get back the scaled version of the data. And let's wrap this in a data frame initializer, because we want to, this actually returns a numpy array, so we're going to turn it back into a data frame after. And I want to keep the indices on the same as they were, and the column names the same as they were. Alright, and then we'll just go and copy this over for xtest. Alright, and let's take a look. Here's xtrain. You can see that all the columns have the same range of values now, and xtest will also. So let's do training. We're going to create our model. This is just going to be a logistic regression model. And we can fit the model to the train set. So xtrain, ytrain. That's it. That was quick. And then our results. So let's first get the accuracy. So on the test set, we'll use model.score, passing in the test set, and that will return back the accuracy value as long as we're dealing with a classification model, which we are. And then we'll get a set of predictions, so ypred, and that will come from model.predict on xtest. Alright, so first thing we'll do is print out the accuracy. Test accuracy, we'll display it to 2 decimal places as a percentage, and format this with acc times 100 since we want to see it as a percent. Then we'll create a confusion matrix. So that's a way of visualizing the classifications. Let's call it CM, and this is a confusion matrix from sklearn. We're gonna pass in ytest and ypred. And we want to specify that the label should go in the order 0, 1, just so we're sure we know the ordering of the labels. Then we'll make a classification report, which will give us some extra information about the confusion matrix. Now we'll call that CLR. That's also from sklearn. Pass in ytest and ypred, and the labels stay the same. Now we can actually give this one some target names. so we can give the labels custom names if we like. So why don't we say negative and positive. Alright, and now let's plot the confusion matrix. So I'm going to create a new pie-plot figure in a 6x6 grid, 6x6 figure, and use the seaborn heat map function to plot our confusion matrix. Turning on annotations so we can see the counts. Setting format equals G like this so that we see it as integers instead of scientific notation. Setting the minimum color value to 0, giving it a color map of blues, and turning off the color bar. Let's just show this so far. Alright, so we have a 75% accuracy, but as you can see, that's actually not so informative because we're not doing so well in the positive class. So I can't, we can spruce up this confusion matrix a little. Let's give it some tick marks. So x ticks, the ticks, this is the spacing. We'll do 0.5, 1.5, which corresponds to the current spacing. And then we'll give it some labels. Let's use negative and positive the way we did. I'll do it like this. We'll use double quotes. Just copy that over. Alright, and we'll do exactly the same thing for the y ticks. So when we're done, we'll just give it some axis labels. The x is our predicted values, and the y is our actual values. And we'll give it a title, which is confusion matrix. We'll also print out a classification report, the one we created. And we will pass in CLR here, and let's take a look. Alright, so we can see our predicted values against the actual values, and you can see that within the negative class we're doing alright. Down here we can see our scores within each class. So the F1 score is sort of a measure of overall how we're doing in the class. So let's look at negative. Precision means out of all of our predictions for the negative class, which are these two boxes, 76% of them were correct. And this is saying we predicted negative incorrectly when it was actually positive. We predicted negative 3,665 times, which was 24% of the time. The recall is saying out of all the actual negatives, which are these two boxes, we got, well, it rounds up to 100. We got 100% correct, so it's like 99 point something. Because you can see we really hardly made any misclassifications within the negative class. However, so the F1 score here is quite good, 0.86, because you can see we have pretty high precision and recall. But for our positive class, we're doing terribly, because you can see a precision as 0.51. That's saying out of all of our actual predictions for positive, we got 51% correct. But that's not saying much because there's hardly any predictions for positive. Our model rarely predicts positive. There's 3,713 positive examples, and we've only made about 100 predictions. So our model is completely failing to spot those positive values. The recall is completely atrocious because it's saying out of all the actual positive examples, we got 1% correct, which is this box. And the F1 score is a combination of the two, an average between them. And you can see it's much more heavily weighted down towards the recall because F1 score is very largely affected by bad scores. Okay, so how can we address this? I'm not going to go full in depth how to address it, but we can try one thing, which is class weights. So when we create the model, we can give it a class weight, which is a dictionary that maps a weight to each class. So in the loss function, we can tell the model to penalize one of the classes, for example, twice as hard as the other. So the way we do this is we map the class to its like a scalar of how much we want to penalize. So by default, it's 1.0 for both of them. And we want to, by raising the amount, we're drawing more attention to that class. We're saying the model should care much more about this class. So we want it to pay more attention to the positive class. So let's try changing the weight to 2. So we care about the positive class twice as much. The model is penalized twice as hard for performing badly on a positive example than it is on a negative. So let's run this again with a new class weight, and then we'll take a look. So actually it's looking a lot better. Our F1 score went up to 0.2. You can see our recall went down a little within the negative class, but that's totally worth it because we are doing better here. Let's see if we can even bump this up more if we get better results. 5.0. Now we're up to 0.42, but it looks like our negative class actually took quite a hit. It looks like all of the predictions are shifting over to positive now. So we want to look for something in between this, maybe 3. And they're getting closer. It's not too bad. We have about the same F1 score on the positive, but much higher on the negative. So this looks like probably a better model. It's still not really getting. We're not getting a great recall in the positive class. So we're not really able to identify positives when they're positive. But our model is definitely predicting more positives than it was before. Maybe 2.5 will be the right balance. Alright, and this is looking probably the best, I would say. Now our overall accuracy certainly went down, but the model's doing its job now. Before we had an artificially good accuracy. Accuracy really doesn't tell you much. Confusion matrix is a much better way of knowing how the model's performing. Alright, and that will sum up today's video. So thank you so much for watching. I hope you enjoyed it. If you did, make sure to subscribe and hit the bell for more content, and leave any comments you have in the section below. I'll see you guys tomorrow. Have a fantastic day.